In this section, we will be studying series and convergence. We start off with an important use of infinite series, which is representing an infinite summation. To do that, we start off with a sequence. So an infinite sequence. So this is going back to section 9.1. In 9.1, we looked at sequences, a sub n, that looked like terms a1, a2, a3, ... And that list went on forever. What we're going to study in this section is what happens when I take all of those a's. I'm going to start on the right side, and I add them up. If I add a1 plus a2 plus a3, and I add up all of those terms, infinitely many terms. So this does not end. And how we represent that is as the sum from n equal to 1 to infinity of the a sub n's. So an infinite sum of all of those terms. A1, A2, fix this notation for me, please. A3 are the terms of the series. Sometimes we may see series that start at 0. Sometimes we may see series that start at 1. So we have to pay attention to what the index is of that series. And we are interested in finding what is the value of that infinite sum if it exists. So there will be times where we add up all of these numbers and it converges to a whole number or to a real number. And there'll be times where it diverges to positive infinity. So how are we going to evaluate what this sum is? In order to do that, we use a sequence of partial sums. A sequence of partial sums. So the sequence that we use is a sequence called capital S sub n. And first I'll just write the notation. The terms of that sequence look like this. Let's be clear what I'm using here. So it's indexed by I equal 1 to n. And on the inside we have a sub I. So what does that mean? That means that S1, the first term of that sequence, means take the sum from I equal 1 to 1 of the a's. So just add up the first a term. But when n is equal to 2, the index on the top of the summation changes to 2. So this is now a sum from I equals 1 to 2 of the a sub i's, which means add up the first term and add up the second term. S3 would mean add up the first, second, and third term. And then the nth term of this sequence would be when I add up the first n terms of this series. Remember, we're interested in finding what happens when we add up infinitely many of these terms. So far, we have built a sequence, and we are at the place where we have added up n of these terms. Hopefully, you're forming an idea of what we're going to do. At some point, we want n to go to positive infinity. Because when n goes to positive infinity, that's how we end up adding infinitely many terms. So if this sequence converges, that tells us that the sum will be convergent, the sum of all of these terms, as n goes to infinity. So we're particularly interested in this expression here. This is the sum of the first n terms of the series. Remember, the series is when we add things up. We made a sequence of S1, S2, S3, S4, Sn. And in that sequence, we're interested in what's happening when n goes to infinity. So in example 1, let's look and see if this series converges. We've already seen, hopefully you watched the video before this lecture showing 2 different ways to evaluate this series. I thought that the way with the square where you were looking at the areas and you took a half and then a fourth and then an eighth and so on and so forth. It gives a very intuitive explanation as to why this series does converge to 1. Hopefully we've already seen that. But let's look at the calculus behind it. So I think that's helpful sometimes to just write out a few terms of the series. It'll also help us form our sequence of partial sums. So when n is equal to 1, we have a half. When n is 2, a fourth. When n is 3, an eighth. 1/16, and so on and so forth. We're interested in what do all of these numbers add up to. Let's form our sequence of partial sums. I'm going to call that sequence S sub n. So to find S1, I only want to add up the first term of the series. That is simply a half. To find S2, I want to add up the first two terms of the series. A half plus a fourth. And a half plus a fourth is equal to 3/4. Then I'll add up the first three terms of the series. I'm going to start writing in my terms of my sequence. So far I've seen that one term of the series adds up to a half. When we add up the first two terms of the series, we get 3/4. When we add up the first three terms of the series, we get 7/8. And I'm going to stop my list here. Ideally, what I'm interested in is what happens when I add up the first n terms of the series. So we found the first, second, third term. What we would like to know is, in general, like, what is the nth term of this series? So it would be nice if we can look at these numbers here in this sequence and try to find a pattern, the same way that we did in section 9.1. Well, when I look at the numerators of 1, 3, and 7, I do notice that those numbers are powers of 2 subtracted by 1. So just a quick reminder, remember that we talked about in section 9.1 that powers of 2 are 2 to the 1 is 2, 2 squared is 4, 2 to the third is 8. Recognizing numbers like this, perhaps it would have been easier to start with the denominator now that I'm looking at it. Because if I ask you to look at these numbers that I circled in gray and to find a pattern, maybe first thing you would recognize is, oh, the denominators are powers of 2, right? 2, 4, 8. And then you look at the numerator and you see 1, 3, 7. Well, that's just one less than the number in the denominator. So 2 to the n minus 1. I want to pause here and point out that in this lesson, one of the skills that you need to have is to be able to start with a series, form a sequence of partial sums. So tell me, what do you get when you just add only the first term? What do you get when you add the first two terms? What do you get when you add the first three terms? So form that sequence, this sequence right here, and then try to find a pattern for what happens when you add the first n terms of the series. So now that we have an expression for when we add the first n terms of the series, remember what we want. We want n to go to infinity because we want to know what is the infinite sum of the series. So the sum from n equal to 1 to infinity of 1 over 2 to the n, what happens when we add up the first, or excuse me, not the first, but what happens when we add up all of the infinite terms will be the same thing as when n goes to infinity if we had added up the first n terms. When we add up the first n terms, we get 2 to the n minus 1 over 2 to the n. So if we can evaluate this limit, then we know what the sum is equal to. So when I look at evaluating this limit, I'm reminded of Calculus 1, where I see a power of 2 to the n to the top in the denominator. So I know that the limit of this is going to be equal to 1, since we're seeing kind of not equal degrees, but equal exponential, equal power functions showing up in the top and the bottom. If you wanted a more algebraic way to think of that, imagine that you came into this expression, this fraction, and you divided each term by 2 to the n. What would we be left with? We would be left with 1 minus 1 over 2 to the n over 1. If we think about what happens as n goes to infinity, this term is going to 0, leaving us with 1 over 1 to get the final answer that this limit is equal to 1. So this sum is equal to 1. All of these numbers add up to 1. So we've now seen both a geometric interpretation and a calculus interpretation. Again, we start this example the same way, wanting to form a sequence of partial sums. And we call that sequence S sub n. So I'm interested in what happens when I add up just the first term of the series. I would get 1 over 1 minus 1 over 1 plus 1, which is 1 minus 1 half. Let's see what happens when we add up the first two terms of the series. So we'll still have the first term, which is 1 over 1 minus 1 half, or I'll just write 1 minus 1 half. Mind you, so just to make sure we're following the notation, all of this just comes from when n is equal to 1. Let's see what happens now when n is equal to 2. So because it's a sum, we add. And then I'm going to go into this expression here. And when n is equal to 2, I would have 1 half, 1 over 2, minus 1/3. Notice then that the negative 1 half from the first term and the positive 1 half from the second term cancel out, leaving us with 1 minus 1/3, which is 2/3. A similar thing will happen if we evaluate the third term. Again, I'll write it the same way because I want to show how these terms are canceling out. So I still have when n is equal to 1, when n is equal to 2. Since we're on the third term of the sequence, I want to see what happens if I let n equal 3. If n is equal to 3, we'll have 1/3 minus 1/4. We still have these 1 halves canceling out, and now we also have these 1/3 canceling out, which leaves us with 1 minus 1/4, which is equal to 3/4. I'm going to start filling in the terms of my sequence of nth partial sums. I have not been writing them. When I added up only the first term, I got a half in total. When I add up the first two terms of the series, we get 2/3. The sum of the first 3 terms of the series is 3/4. So when you look at these numbers, this 1 half, this 2/3, this 3/4, what would you guess if this is S1, S2, and S3? Do you see a pattern to figure out what Sn is? So it looks like when we calculate Sn in general, the numerator is n. In S3, the numerator was 3. In S2, the numerator was 2. In S1, the numerator was 1. And the denominator is always 1 more than that. So in general, it looks like the nth term of this sequence of partial sums is n over n plus 1. In order for us to find the sum of this series, what we need is the limit as n approaches infinity of S sub n. I'll write S sub n first. So just to be clear, I'll go back and start with the summation notation. This is what we're trying to find. What happens when we add up all of these numbers, infinitely many of these numbers? We know by definition that we can evaluate that by asking the question, what happens when we take the limit as n goes to infinity of just the first n terms? So don't add up all the numbers, add up n of them, but then apply a limit as n goes to infinity. We had to do a little bit of work off to the side over here to come up with an expression for when we add up the first n terms. We've said, oh, generally speaking, when you add up the first n terms, you get n over n plus 1. And when we apply a limit as n goes to infinity of that, this goes back to Calc 1. This is Math 271. When you're applying this limit, you should be noticing that the degree of the denominator and the degree of the numerator are the same. So I need the ratio of leading coefficients, which in this case is 1 over 1. So this limit is equal to 1. And I can conclude that this series converges. This is called a telescoping series. A series is called telescoping when we have this canceling out that is happening. Notice with the 1/2 and the 1/3, the numbers that I have circled in gray that we can see canceling out. Telescoping series behave like this with this canceling in here. So ultimately what ends up mattering at the end of the day is what was the first term of your telescoping series, your b sub 1, if I follow this notation here, and then what was the last term. So let's think about that, how that last term is written. If I'm adding up the first n terms of a series and it's telescoping, the terms look like this. Telescoping series look like this, where they have these two terms that are being subtracted. So here I have the first piece of the series, the second piece of the series, the third piece, so on and so forth. When I get to the nth piece, I would have been adding bn minus bn plus 1. Now, if we keep following the pattern of a telescoping series, I'll go back and point out what's canceling. This canceled with this. The B3 canceled with the B3. The B4 canceled with the B4. You can't see it, but the B5 will cancel with the positive B5 in there. And this Bn will cancel with the negative Bn in the term before it. So all that's left is the Bn plus 1. So generally speaking, when we are working with a telescoping series, if we can find this expression, then we have our S sub n. Example 1c is also a telescoping series. It does not look like it right now, because first we need to take the expression that is on the inside of the sum and decompose it using partial fractions. So a quick refresher on partial fractions from, I believe, section 8.5. We start off with 2 over 4n squared minus 1. First step of partial fractions is to completely factor your denominator. I have a linear factor and another distinct linear factor. We need to set up a system of linear equations or use particular n values in order to solve for a and b. So I won't talk through it, but following through the same process we went in 8.5, I will solve for a and b. Clear out my denominators. And I conclude that a is equal to positive 1 and b is equal to negative 1. So now I can rewrite the series. as 1 over 2n minus 1 minus 1 over 2n plus 1. And now let's look and see what happens when we add up the first n terms of this sum. I'm not going to break it down into S1, S2, S3. I'm going to just start off and write just the first n terms. So when n is equal to 1, we would have 1 minus 1/3. I will point out here, this is just when n is equal to 1. Now when n is equal to 2, we will have 1/3 minus 1/5. When n is equal to 3, we will have 1/5 minus 1/7. Dot, dot, dot. Let's go on to think about what happens when n is equal to n, when we add up the first n terms. Well, then I'll just have a 1 over 2n minus 1 minus 1 over 2n plus 1. Okay, now let's look and think about what cancels out in here. The negative 1/3 cancels with the positive 1/3. The negative 1/5 cancels with the positive 1/5. The negative 1/7 will cancel with the positive 1/7 that you can't see. And this 1 over 2n minus 1 will cancel with a negative 1 over 2n minus 1 back here that you also can't see, leaving you with only the first and the last term. So we know that S sub n is equal to 1 minus 1 over 2n plus 1. Now that we have an expression for S sub n, to get our answer, we need to think about what is the limit as n goes to infinity of S sub n. And that limit is equal to 1 because the second term goes to 0, since the degree of the denominator is more than the degree of the numerator. Again, that's going back to Calc 1, thinking about how to evaluate these limits of rational expressions. In example 1D, we have the sum from n equals 1 to infinity of just 1. Let's take a look at what the nth partial sum of that series would look like. If I add up just the first term, I would just add 1. If I add up the second term, 1 plus 1, which is 2. For good measure, if I add up the first 3 terms of the series, I would get 3. We can, I hope, see that if we add up the first n terms of the series in general, we would get n. Now that we know what the sum of the first n terms of the series is, what happens if we let n go to infinity? The limit as n goes to infinity of n is equal to infinity. And so we conclude that this series diverges. And it does make sense that if we add up 1 infinitely many times, we will get infinity.